Okay. Yeah, okay. Yeah. My mold day shirts. There will be a mold day event, I think so. They're going to call it Sci-tober, so you can... There's only a few more slides in chapter 11, and I don't even know what they are, but we got this far talking about a benzene ring as a substituent, and it is called a phenyl group. We got that far. Not to be confused with a phenol molecule in aromatic alcohol, and we'll see that in chapter 12, this aromatic alcohol. Okay, the heterocyclic aromatics, chapter 20. But just to make the point that aromatic molecules, well, make 2 points. Aromatic molecules can contain carbon and nitrogen. That's where you get the heterocyclic. This isn't benzene with just carbons in the ring. Carbons and nitrogens. But even with carbons and nitrogens now, you have these alternating double bonds, and it is aromatic. Has an aromatic character to it. And these are very, very critical. These are very, very critical ring structures to DNA and RNA. Purine, pyrimidine rings are in adenosine, guanosine. Are you okay? You're making me feel self-conscious.
It's not you, I promise.
Oh, good.
It's her.
Good.
It's me.
I usually don't feel self-conscious very long. So there's benzene. Okay, this is a reaction you need to know. You need to know this reaction. Benzene plus chlorine. And why is this kind of a little unusual, or could get you a little bit confused? There's a double bond. There are double bonds in this benzene. And you might be tempted to think that the chlorine will add across that double bond. And if you are tempted to think that because of what you've learned about alkenes, that halogens add across a double bond and you get a bromine on each one of the double bonds, you couldn't be criticized for thinking that way. But the aromatic does not react like an alkene. It undergoes substitution. A chlorine takes the place of a hydrogen, and a hydrogen comes onto the chlorine. A whole lot like alkanes react with halogens. This is a substitution reaction. It is halogenation, but it's halogenation that's proceeding by substitution. So this is going to take the place of the hydrogen, and the hydrogen is going to take the place of the chlorine. Okay, substitution, and then you get this ring structure with the chlorine on it. One chlorine. And it's still aromatic. Look at that. It maintains its aromaticity. So if you look at the reaction summary for chapters 10, 11, and 12, this is one of them on there. Halogenation of an aromatic. I'm not going to dwell on it, but just it is one that I expect you to understand. The FeCl3 here is just a catalyst. That's just a catalyst catalyzing this reaction. And I think, all right, this is just summarizing the reactions. There's your, there's your 4, I'll just put here, 4 addition reactions of alkenes. And the 4 all are geared around the reactant. These 4 different reactants. And what are we doing? We're adding them to a double bond. Hydrogen, water, a halogen, or a hydrohalogen. So that's just a summary. There's a list. We talked about polymerization, and then just put here the halogenation of an aromatic. That's kind of the major summary of chapter 11, reactions, and then that's it. Okay. Okay, let's get into alcohols. Okay, alcohols, we're adding oxygen. This is the first instance of an oxygen coming into a carbon. So we've talked about all hydrocarbons in chapter 10 and 11, and now we're adding oxygen. And we get this OH group, hydroxyl. This is actually ethanol right here. And this is the alcohol that's in alcoholic beverages. Ethanol. We call it alcohol. Chemists would say that's pretty, using those words in a sloppy manner. That is an alcohol. And it is sloppy, meaning some people thought, hey, I can drink any alcohol. And they threw any kind of alcohol in water, 100 years ago, and had very dire consequences, because not all alcohols are necessarily good. And this one is not necessarily good. I just tell you, I hate to inform you, but this one isn't necessarily good either. There's more and more papers coming out about the interaction, the effect, the increased risk of various things as a result of alcohol. This alcohol. All right. That bond, that OH bond, is a polar bond. Now remember, 10 and 11, I said hydrocarbons are nonpolar. All of a sudden now we're looking at an organic molecule that has a functional group on it that is polar. Because water is made up of 8 hydrogen and oxygen bonds. And you get a negative towards the oxygen, a positive towards the hydrogen. And so what happens is that another water molecule comes along here and is attracted. So a water molecule is attracted to another water molecule by what we call hydrogen bonding. And it's always the negative oxygen orienting itself near the positive hydrogen. That's a hydrogen bond. Opposite charges attract. So to write it this way is wrong. This would be the wrong way to write it. Those two repel each other. And you've taken magnets, and I think you've probably done this. You've taken magnets and you move the north end of one magnet towards the north end of another magnet. And the north end of the other magnet starts moving. It starts moving away, and then it'll flip around and come together, right? Have you seen that happen? So the north poles of the two magnets repel each other, and actually, if you really try to force them close to each other, the magnet will spin around, and the north pole will align with the south pole, and they will slam together. That's what will happen to these molecules. If these molecules come near each other like this, they will flip to be like that. You follow me? This will repel. That will repel, and the molecule will actually chink and go into that hydrogen bond. It won't make that noise. I like sound effects. I mean, when they came out with movies that actually had sound, I loved it. No, I wasn't back then. I'm not that old. I had you going for a minute. Okay, you got it? That's hydrogen bonding. That's how these molecules are behaving. So now, you come along with this kind of a bonding. Okay, yeah, we have an oxygen bound to a carbon, but we have an oxygen bound to a hydrogen. And the same thing happens here in that OH bond that happens with an OH bond in water. It is a polar bond. And so what that means is this: you put this in water, if you put this in water, that alcohol, that end of the alcohol molecule that has the OH group on it, can form hydrogen bonds with water molecules. Hydrogen bonding. So that end of the molecule is polar. That doesn't mean the rest of the molecule is polar, but it means that end of the molecule is polar. It also means that if I just had a bottle of the alcohol, no water at all in there, they can hydrogen bond with each other. So the effect of this is that it increases the effect of the alcohol molecule interacting with water molecules. It increases the solubility of the alcohol in water. And what is the effect of this? The effect of this is it increases the boiling point of the alcohol. If you were to compare that alcohol with a similar hydrocarbon of similar molecular weight, you would find this had a much higher boiling point because it has these intermolecular attractions to one another, requiring a lot more energy to get them to boil. Okay, now let me take this out of the realm of the abstract and the verbal, and just kind of show you. I gotta point out one other thing, and then I'll demonstrate it. Okay, so yeah, here's showing the boiling point trends. Here is propane. Here is propanol. Forget this one in the middle right now. That's dimethyl ether. Forget that one. The main comparison I want to make is between this alkane and this alcohol. And why am I comparing those two molecules is that they are similar molecular weights. They weigh about the same. They're about the same size molecule. But this one has no opportunity for hydrogen bonding. These molecules are non-polar. The carbon-hydrogen bonds are non-polar bonds. So there's no polarity in this molecule. But this is ethanol. This is ethanol. And it's got this oxygen-hydrogen bond right here, allowing it to be attracted to the oxygen-hydrogen bond of another ethanol molecule. And look at the difference. Add those up. That's 0, it's 11, 12, 120 degree difference boiling point. Propane is a gas at room temperature, and ethanol is a liquid at room temperature. Hasn't even started approaching its boiling point yet. That's not room temperature. That's 78 degrees centigrade. That's about a little bit cooler than a McDonald's coffee. Hot to boil that. You see that? And that is because this ethanol molecule can hydrogen bond to another ethanol molecule and another ethanol molecule. Those hydrogen bonds have to be broken before that molecule will vaporize into a gas. And it takes energy to break those hydrogen bonds. Okay, so that's what's happening on boiling point side of things. Let's see what's happening on the solubility side of things. Okay, let's, and the ones that, there's a lot of data on this slide, so again, look at that. Here's ethanol again. 2 carbons, 1 OH, and it's very soluble in water. We're talking about a mixed drink. You make a mixed drink with whiskey and water, and the whiskey isn't floating on top of the water. It's dissolved in the water. Why? Because that alcohol is soluble in water. But as you start moving up, this only has 2 carbons. If you go to butanol, and we'll get into naming in a minute, but that's what this is. This is butanol. And you might have already, you probably do like to run ahead and try to figure these things out, and you may have already done that because that's got 4 carbons and it has an OH, so it's butanol. The chain has gotten longer, but the solubility is decreasing. It's not as soluble in water as ethanol is. So, are alcohols more soluble in water than alkanes? Yes. But the story isn't as simple as saying alcohols are soluble in water. It depends. What does it depend on? It depends on the length of the chain, how many carbons there are, and how many OHs there are. And if right now we just think about 1 OH on an organic molecule, here we are 1, 2, 3, 4, 5, 6, 7, and this is not soluble in water. That's, what's the name of that one? 7 carbons. Heptanol. 7 carbons. Not soluble in water. Is it an alcohol? Yeah, it's an alcohol. It's got an OH. Is the OH polar? Yes, it's polar. But there is too much non-polar character to this molecule to drag all of that into the water. For this end of the molecule to overcome all of that non-polar nature to the molecule, and so it's not soluble in water. Okay, let's look at this. I love this slide, okay? I love this. I like it, okay? Let me put it that way. Let's not get carried away. I like this slide. Okay, so what do we got here? Number of carbon atoms in a molecule, 0, 1, so that's just 1 carbon, 2, 3, 4, 5, 6, 7. So we were just talking about a molecule with 7. Solubility in water, in grams per 100 milliliters of water. So we're doing a controlled experiment here. We're taking 100 milliliters of water, and we're seeing how much of these different compounds we can get to dissolve in that water. The red line is alkanes. There's no OH here. So 1 carbon, what molecule is that? If you're reading this slide now, you have to say, what is this slide telling me?
Methane.
Methane. And what molecule is that? 5 carbons. Pentane. So it really doesn't matter how many carbons you have for alkanes. They're not soluble in water. How much? Maybe about 0.2 of a gram in 100 milliliters of water. We're not saying that you can't get any of it in the water, but we wouldn't call that soluble. Follow me? You could add 10 grams of pentane to 100 milliliters of water, and 9.8 grams are going to be floating on top of the water. And a little bit is going to be in the water. So if you got gasoline in contact with the water, don't drink that water. There is some gasoline in the water. A little bit. But we say not soluble. Okay, now let's look at alcohols. And this is grams, and we're starting here, what we can see is 8 grams per 100 milliliters of water. Methanol is so far off the charts, we can't even see it. It's what we would call miscible. It's infinitely soluble in water. You you could put 1,000 gallons of water in 100 milliliters. And, the water's going to... Ethanol, miscible. Propanol, it's probably up there. I don't know where it would be, but it's 30, 40 grams per 100 milliliters of water. Butanol, about 8 grams. The solubility is starting to decrease. As the chain length increases, pentanol, hexanol, heptanol, solubility decreases. You see that? By the time you get to 7 carbons long and an OH, it's behaving just like an alkane. It's just as insoluble as an alkane.
So as the chain length increases, the solubility
decreases. Yes, exactly. Okay, so here is water. Here's water. And let's just take, I won't even measure it out. We'll just take some water. That's too much. Too much. Yeah, that look pretty good. Okay. And here is methanol. Methanol. Let's get this up here. Methanol. And there's water, methanol. I'll put a couple good healthy squirts of methanol in there. Mix it up. It looks a little hazy right now because of all the air I just blasted into it. But the air is going out and it is soluble. Yes? Can everybody see that? I'm trying to get a bigger test tube here. Soluble. Methanol is soluble in water. Okay, alcohols are soluble in water. Well, let's test another alcohol. This one is 1-octanol. 1-octanol. So, here's our water. There was our methanol. So here's our water. Let's take a couple squirts of 1-octanol. I've always showed this slide, but I've never kind of showed it. So here's 1-octanol. 1, 2 healthy scoops in there. Want me to do 3?
Yeah.
Okay, I'll do 3. 3? More the merrier?
Oh, yeah, you can see it.
Oh. This is an alcohol, folks. That is an alcohol. Is it soluble? No, it's not soluble. Not soluble. If it was soluble, these 2 columns of liquid would converge and make one solution. It's not making one solution. It's remaining as 2 separate compounds, water and alcohol.
Is that why vodka doesn't freeze?
Is that why what? What does it freeze?
Vodka, alcohol.
Well, it'll freeze, but it won't freeze at our temperature. You've got to get it colder. It will eventually freeze. It just has a lower freezing point than water. I have no idea what. There's something else going on there with alcohols because they have something dissolved in them, and whenever you dissolve in anything in water, you lower its freezing point. Okay, and that would be the same way with the alcohol in there. You put water in alcohol, and it's going to lower the alcohol's freezing point. So you're not getting the freezing point of alcohol. You need pure alcohol, and then try to freeze it, and then you would know what its freezing point is. So no, this doesn't have anything to do with the freezing point. It just has to do with solubility. Okay, all right? So, bottom line, alcohols are soluble in water. Well, whether alcohols are soluble in water or not depends. And it depends on a couple things. One thing it does depend on is the chain length. Now on your homework assignment, you're going to be challenged to think about this a little bit. It's going to give you two molecules, and one is real long and has an OH on it, and another one is just as long, but it has 4 OHs on it. And it's going to ask you to think about which one of these is soluble in water, and which one, etc. Okay, so that's enough there. I think I made the point about boiling points and solubilities. All right, nomenclature. We definitely need to get into nomenclature and hopefully even into some reactions if we can. A lot of the background here you're familiar with. Chain length, you count the number of carbons and you come up with a name. It's methyl, ethyl, propyl. Actually, the IUPAC name is going to be meth, eth, prop, ethanol, propanol. These are common names up there. Methyl alcohol. It's not the IUPAC name. It's a common name. Ethyl alcohol, propyl alcohol. And you are going to start numbering where the closest to where the OH is. Okay, so let's take a quick example. Here, rule number 1. What's rule number 1 always? Find the longest chain. I don't care what organic compound you're talking about. Find the longest chain. 1, 2, 3, 4. Now, start numbering from the end closest to the OH. Since you are going to put that functional group in the parent name, butanol, then you need to give that precedence for deciding where you start counting carbons. So that's 2-butanol. That's where you would start. And then you would say, okay, what did I leave out? I left out that methyl. It's on carbon number 3. So the IUPAC name is 3-methyl-2-butanol.
So it's because it's 4 carbons and it's an OL because of the OH.
Yeah. See what we're doing? We're taking this alcohol. All right? That's where we're getting that OL off of the last 2 letters in the word alcohol. So you see an organic compound that ends with an OL, and at least you know there's an OH in there somewhere. There may be other stuff, but there is an OH in there somewhere. 2-butanol.
And then
How would we do what, Whitney? How would you do the line formula? Okay, well let's see the line formula. Butanol. So I got 1, 2, 3, 4. I would put an OH right here and a methyl right there. Or if you want it to look like that molecule up there, you can put the OH down here and you can put the methyl right there.
So we will always put the OH. You can't just draw the line, you have to
write an OH. Right. Remember, that is a methyl group. There's a carbon at the end of that line. There's not a carbon at the end of this line. There's an OH group at the end of this line. A hydroxyl. That's a hydroxyl group. Yeah, good question. So there's your, and then someone might say, okay, what about the condensed formula? Okay, because it is an OH and there are 2 atoms there, slap a parentheses around it. Do you have a question?
I want to see the line diagram really quick.
Okay? All right, cyclical ones. Okay, now, if that were not there, you'd call that, methyl cyclohexane. But that OH is there, so it's going to be cyclohexanol. You drop the E and add OL. Cyclohexane becomes cyclohexanol. Because there is an OH there, that designates that as carbon number 1, 2, 3. And we're going to count to the... I'm going to try to lower my volume. I don't know that I'm going to be able to talk the rest of the day, but I will lower my volume a little bit. That may be great. I probably should speak lower anyway.
It felt like you were yelling at me. So just
Okay. This is all on tape. So you count in the shortest distance to the other substituents. All right. So we got 3-methyl cyclohexanol. Okay. All right. Here are 2, and I'll just put right here. You should have 3x5 cards for each one of these. These are the common names. Let's take this one first, because this one is the most common one. Isopropyl alcohol. Now notice that you have an isopropyl kind of a group right there. You have the OH bound to the middle carbon, which is where the isopropyl group, the isopropyl substituent, would bind to something. Here it's bound to an OH group, so we call it isopropyl alcohol, or it would also have the name isopropanol. How do you spell that? Propanol. So let's go down to the bottom and see what would the IUPAC name of this be. Now forget those common names. Use IUPAC rules to name that.
Are you going to want us to, like the isobutane, are you going to want us to know like the iron acids are that
Yeah, that's why I'm saying 3x5 cards. You need to memorize
that isopropyl alcohol is named as isopropyl and the IUPAC.
Can you explain the T?
Well, let's get to that in a second. Let's finish off this molecule. 2-propanol. Longest chain, 3 carbons, so it's propanol. And the all is, it's on the 2. Is that what you said? 2-propanol? Yeah, 2-propanol. It's on the second carbon. It doesn't even matter which side you start counting from. You get to 2. That's 2-propanol. And let me give you one other name of this. This is rubbing alcohol. And just another example of an alcohol that is not ingestible. It's alcohol, but we don't ingest rubbing alcohol.
So in the homework, it's asking for the common name of it. So do we put the isopropyl alcohol?
Yeah. I would accept isopropyl alcohol or isopropanol, and probably even rubbing alcohol. Rubbing alcohol is the very, very common name of it. It's the... Okay. So that's a molecule with a whole lot of names. It's a very common alcohol. Use it in the hospital to disinfect the skin. I'm not sure if that's what they use before they give you a shot or not. Is it? Rubbing alcohol? It's rubbing alcohol? So, right. Yeah, so it's killing the bacteria and topically applied, not ingested, but topically applied. Okay, now Whitney, let's get over to the T-butyl alcohol, or tertiary butyl alcohol, or tert butyl alcohol. You can see the tertiary butyl substituent there, but it has an OH on it. What is the IUPAC name of it? Okay. Okay, several of you have said it. 2-methyl-2-propanol. Okay, you see the longest chain is still 3 carbons. The OH is on the second one, and there is also a methyl there. So 2-methyl-2-propanol. That's tertiary butyl alcohol. So methanol, colorless and odorless, toxic, can cause blindness and death if ingested. Ethanol, an odorless and colorless liquid widely used as a solvent, the alcohol in alcoholic beverages.
Professor, I have a question.
Yeah.
So when you are looking at it, if the OH is, it's always going to be number 1, right? Like you start closest to the OH.
Right.
So then if OH is at the X, would you put 1, I mean, you would put like 2-methyl-1-propanol? Or like, would you?
Yeah. Let's see. Yes, you would still put 1. That's a good question. So what Hannah is asking, let's say we had an OH here, and we had a methyl here. I'll just write it as a methyl. Okay, you have to put a 1. Even though it is on the first carbon, if you just say that that's 2-methyl-propanol, I'm left in some confusion as to whether that OH is on the first or the second carbon. So you have to take that confusion away. This one is 2-methyl-1-propanol. And I know this is a little confusing because on a couple occasions I said, you don't need a 1 here, you do need a 1 here. Well, how do you know? Well, that OH could be here. If there's a molecule, I got to put it back because I got the name underneath it there, but it has 2 possible locations. So whenever it has 2 possible locations, you need a number. If I had cyclohexanol, and you say, well, couldn't it be here? Well, yeah, it could be there, but that's no different than if it was there. Those carbons are all 6 identical carbons. Okay? So that is where I don't need a 1.
If it was on the cyclo.
On the cyclo. You can just say cyclohexanol. But then if there is a... Okay, that's enough.
So it reacts just as if it was
That's enough.
like the cyclohexane.
Water's muddy enough right now. Yeah, yes?
It would just be like cyclohexane where you wouldn't have to put exactly where it starts.
Yeah. Okay, now what's the next slide? Okay, just these propanol, rubbing alcohol, a disinfectant, a astringent, an industrial solvent. When I was in industry, we ran reactions with isopropanol as our solvent in some of the reactions. Okay, this is antifreeze, extremely poisonous. This shuts down the kidneys, probably damages the livers and shut down the kidneys, and it's sweet. This molecule is sweet. Don't taste it. This is why it's not a good idea to spill antifreeze around dogs and cats and things like that. It will harm them. And they will like it. I mean, they won't like being harmed, but they will like the antifreeze.
There was a lady that came out on TV that she killed her husband by putting antifreeze in his ice cream.
Don't do that either.
Don't do that either.
My cousin's neighbor killed their dog like that. They put meat and antifreeze into it.
They will burn in hell.
Well, let me tell you some even more malicious things there. And this has happened, and if you wanted to, you could go Google this. You could find 5 years ago, maybe 20 years ago, even in this country 30 years ago, people putting this into cough syrup formulations, antifreeze, because it is sweet, it's cheap, and whether they knew that it is that toxic or not, I don't know. I probably did. They did. But they cheapened down their formulation by putting antifreeze in cough syrup. Minnie's shaking her head right there.
I've tried some of these stories of people killing bear.
Yeah, I don't know why I mentioned this. I don't want to give anybody this. Okay. Be careful with this. You spill it. Don't lick antifreeze if you can see it on the side of your car or anything like that. Okay. We'll get to this molecule. You will learn this molecule in Chapter 17. This will become one that you have to learn. 1,2,3 propane triol, glycerol, or baby oil. This is baby oil. All right? You go get a little bottle of this. It's kind of viscous. Looks like honey. All right, I'm not going to dwell on those right now. Okay, you need to learn about the classification of alcohols. We're going to be talking about primary alcohols, secondary alcohols, and tertiary alcohols. You need to learn how to identify them. When we start talking about reactions, for example, the oxidation of alcohols, they react differently. They don't all react the same. They all three react differently, primary, secondary, and tertiary. So before you can understand their differences in their reactions, you need to know how to identify them. You need to be able to look at an alcohol and say, oh, that's a primary alcohol, that's a secondary alcohol, and that's a tertiary alcohol. All right, for no extra charge, I'm going to tell you how to figure that out. All right, so here are some primary, secondary, and tertiary alcohols. First of all, methanol doesn't fit in this classification. It is unique. It's none of these. It's the simplest alcohol you can think of. 1 carbon, 3 hydrogens, and an OH, methanol. But let's move on from there to ethanol. What you're going to do to figure out what class it's in is look at the OH look at the carbon the OH is on, and ask yourself how many carbons are attached to it. How many carbons are attached to this carbon? 1. It's a primary. 2-propanol. We were just talking about 2-propanol. Propyl alcohol, isopropyl alcohol. How many carbons are attached to the carbon that contains the OH group? It's a secondary alcohol. You with me? Don't make this any harder than it is. There's an OH on this carbon, and we're talking about 2-methyl-2-propanol. How many carbons are attached to that carbon?
3.
1, 2, 3. It's a tertiary alcohol. What is the common name of that alcohol? Tertiary butyl alcohol. That's what that's called. This is T-butyl alcohol. All right? So now you know where it's getting its tertiary name. It is a tertiary alcohol.
What if there are multiple, like, OHs? Is that possible?
Yes. And as a matter of fact, your homework has one with 2 OHs on it.
I'm not trying to answer, I'm just more curious.
Yeah.
Would you still just look at it?
Each one. And say, what are each one of these the same or different? And if they are different, then say this one is primary and that one's secondary. Okay. Okay, let's take a look at these. Here's 4 molecules, and all we're looking at right now is classifying them. All right, A up there. Primary, secondary, or tertiary?
Secondary.
Secondary. So A is secondary. B. Tertiary. It's kind of leading you down the path here, isn't it? C. Primary. It only has 1 carbon attached to the carbon that contains the OH. Now here is a cyclical alcohol, cyclobutanol. That's cyclobutanol. How many carbons are attached to the carbon that contains the OH?
It's only 2 because they're directly connected to.
Yeah, so there's 2 of them, and that's secondary. Okay, now smarty pants. Now that you know everything. Here's a cyclical alcohol. Here is a cyclical alcohol. And what class alcohol is this one? Tertiary.
Why?
Because it's connected to the methyl and the carbon.
There's your 3rd carbon right there. Okay, so you can't just say that any cycloalcohol is a secondary alcohol. What you can always do is look at this carbon right here and count the carbons attached to it. And you come up with, that's a tertiary alcohol. Because what they do, it replaced one of the hydrogens on there with a methyl group, which had another carbon attached to the carbon that the OH group had on. Okay. All right, go ahead and name those alcohols. In just about 2 minutes. I'll give you about 2 minutes to name those.
So you want us to name it and put the classification, or just name it?
Well, name it. Yeah, name it. Maybe we won't do all 4 of them. Okay, the first one, they've actually numbered out the carbons. So what's the parent name? Hexanol. And where is the OH? So it's 1-hexanol, right? And what else? 5-methyl. You are smarty pants. Okay, the second one, how long's the chain?
5. 4.
Oh, you mean the second one on the right over there?
Oh, yes.
Yeah, 5. Okay, so 1, 2, 3, 4, 5. So that's what, pentanol?
2 methyl, 2 pentanol.
So it's 2 pentanol. Let's get that out of the way. And what classification is that? It's tertiary. That's a tertiary alcohol. There's a carbon, there's a carbon, and there's a carbon attached to this carbon right here. So that's a tertiary alcohol. Okay, and that's probably good enough. This 1, 2, 3, 4, 5, 6, 7. So that's heptanol.
Yeah, 5-methyl 2. Oh, for the last one, is it? Isn't it 1, 2, 3?
So this is a carbon, this is a carbon, and this is a carbon.
So would it be 1, 2, 3 propanol?
Propane triol. And I guess there would be an E in there. You'd bring the E back in because you got two consonants right next to each other. Triol. Just like we talk about hexadiene, this is a triol. Or ethane diol is antifreeze. Okay, that's enough. Okay, let's go right across the right from left to right. Primary, secondary, or tertiary?
Before you move on.
Yes.
What the 1, 2, 3 trial? What degree of would it be?
Well, this one is a primary, and this OH is a secondary, and this OH is a primary.
So then, what would you say? Like if you have
I'd say this is a complicated molecule.
it's complicated.
All right? But there's two different kinds of OHs on this molecule. And they're going to react differently. Well, a little bit differently, but they could all react.
So we would just label it like that if you had one like that.
Yeah. Label which one's primary and which one's secondary. Okay. This is primary. What's the next one? Secondary. The next one. Secondary. There's only this carbon and this carbon attached to that carbon. There's an H. You see that H right there? So that. Okay. The third one, fourth one.
That is secondary. Secondary.
Primary.
The methyl is kind of directly attached to the carbon that's attached.
Yeah, look at this. This OH is on that carbon. That carbon only has one carbon attached to it. So don't worry about all the rest of the molecule. Just say how many carbons are attached to that carbon. One, directly attached. Directly attached. Now over here, that's tertiary. That one's tertiary. Okay, I know I'm moving a little bit fast. Okay, where are we here? Okay, we can get through two reactions. The very first one is the last reaction we left in chapter 11. The hydration of alkenes produces alcohols. So if you were asked, what's one way to prepare an alcohol? By the hydration of alkenes. All right, so you know this reaction, and you need to understand Markovnikov's rule. And if you hydrate propene, the major product is right here. Major product, the OH goes, the hydrogen goes to the carbon with the most hydrogens, and the OH goes to the other carbon. So this is Markovnikov's rule. The hydrogen is going to go to the, so you know that already. I'm not going to dwell any more on it than that. But come back and review it. That's the first reaction in chapter 12. last reaction, or one of the last reactions we studied in Chapter 11. It's the first one we come to in Chapter 12, and it's on your homework. It says, give me the major product of the hydration of this alkene, that alkene, that alkene, that alkene. What is the major product? Okay, I'm going to come back to this one. Let me see if I can. I don't know if I can cover oxidation in 3 minutes. Oxidation is, let me, since we just talked about the classification of alcohols, I'll mention this real quickly, and we'll start here on Wednesday, and then finish up in a half hour. We'll finish Chapter 12, hopefully, and then you'll be able to finish your homework. Okay?
Our homework is due the day of the test, correct?
No, it's due Wednesday. The end of the class on Wednesday. Okay, now oxidation. And I'll tell you what. Yeah, this gets a little complicated too. Let me just lay out in 2 minutes what the results of this are. And we're going to depict an oxidation like this. This is going to be an oxidizing agent. That symbol right there. What is that symbol? That symbol is not taking the place of oxygen. That's not O2 oxygen. That is some sort of an oxidizing agent. Those of you that were in 1107 lab this morning, or will be in it on Wednesday, will see potassium permanganate right here. This is an oxidizing agent. And so we would just write it that general way. And I want to just, I won't go into the details right now, but if you oxidize a primary alcohol, you get an aldehyde. And if you want to kind of get familiar with these things before Wednesday, you'll understand what I'm saying a little better. A secondary alcohol oxidizes to produce a ketone, and a tertiary alcohol does not oxidize. Can't oxidize a tertiary alcohol. So I won't go into any more detail than that, but that shows you, it drives home, I think, the point that you need to be able to distinguish alcohols as being either primary, secondary, or tertiary, because when I say complete the oxidation reaction of this alcohol, the very first thing you're going to have to do is figure out what class it belongs to. And then you will be able to figure out what it will produce. Okay? So we'll come back to this, we'll flesh this out, and a couple more reactions. We'll have to flesh out a couple more reactions. And you will have at least 15 minutes on Wednesday to tidy up your homework and turn it in after I finish the reaction. Maybe this afternoon. But see, I do this lecture twice, and then I kind of decide which one covered it best, and then I decide which one to post. So I'm not, your class doesn't have exactly the lecture I gave you. It's the best one, I thought.